Let's look at some lipid digestion. So of course digestion is going to start in the mouth. So let's scooch all the way up to the top. With lipid digestion in the mouth, we have our lingual lipase. Lingual lipase is able to digest the SN3 fatty acid on triglycerides only up to 12 carbon, short medium chain fatty acids, so up to lauric acid. Cannot touch SN1 or SN2 fatty acids, and it only digests triglycerides. So no phospholipid digestion or cholesterol digestion occurs in the mouth or in the stomach, because in the stomach we have the ability to emulsify. We emulsify due to peristalsis, as well as a lot of the phospholipids and polysaccharides that we also have in the stomach. And then we have one lipid digesting enzyme in the stomach that's called gastric lipase that does the exact same thing as our lingual lipase. It's able to digest the SN3 fatty acid on a triglyceride only if it's short or medium chain length. It cannot digest long chain fatty acids, so only up to lauric acid. Again, no phospholipid digestion, no cholesterol digestion in the mouth or in the stomach. That only happens in the small intestine. So in the small intestine, we have a couple different things that are going to be dumped into the small intestine. We have bile coming in from the gallbladder. We have our pancreas is dumping in a bunch of our enzymes. But there's no brush border lipases, which is a big thing to note. That lipid digestion mostly happens in the small intestine, but it is due to those pancreatic enzymes. So if someone has pancreatic dysfunction, it's usually going to manifest as inadequate lipid digestion or lipid malabsorption. So some of the enzymes that we have secreted from the pancreas include, we have active pancreatic lipase. In order for active pancreatic lipase to become active, because it's secreted in the inactive form, we need a couple different things. We need colipase, which is secreted in the inactive form as well as procolipase. Colipase is going to be activated by trypsin. You remember that trypsin was not active either. It was secreted as trypsinogen that was activated to trypsin through the activity of enteropeptidase, the brush border enzyme. And that's just review from our protein section. So our pancreatic lipase, in order for it to become active, we need colipase, we need bile, and we need the cofactor of calcium. Our pancreatic lipase, once it is active, it's able to digest triglycerides, and it's going to remove the SN1 and SN3 fatty acids. It does not matter the chain length. It can remove short, medium, or long chain fatty acids from the first and third position. It cannot digest the second. It can also remove the SN1 fatty acid from diglycerides that were produced in the mouth or in the stomach. So now we will yield a monoglyceride, either from that triglyceride or the diglyceride, which is just that glycerol backbone with the SN2 fatty acid still attached. And we have removed some other fatty acids, so we end up with some free fatty acids instead. Other enzymes secreted from the pancreas include phospholipase A2, which is secreted in the inactive zymogen form as prophospholipase A2. A2, if you recall, is able to digest the SN2 fatty acid on phospholipids. So it's going to digest phospholipids. It's able to remove the SN2 fatty acid. Cannot remove the SN1 fatty acid, and it does not touch the phosphate or the polar head group on SN3. The last lipid digesting enzyme that we have is esterase. Esterase is secreted from the pancreas, and it's able to digest cholesterol, as well as vitamins A and E, your vowels. Vitamins A and E can be toxic if they're found free, so the storage form of it that's usually found in food is a fatty acid attached to it, or a lot of times it's vitamin A palmitate or vitamin E palmitate. So what esterase will do is it will take these storage forms of cholesterol, vitamin A, and vitamin E and remove a fatty acid to yield free cholesterol, free vitamin A, and free vitamin E. Now all of these products, the fatty acids, the monoglycerides, oops, sorry, with our phospholipase A2, I didn't do the products. We get lysophospholipids. Which are just digested phospholipids. We've removed a fatty acid from them. So we get fatty acid, lysophospholipids, more fatty acids. Let's see, we have monoglycerides, more fatty acids. So all of these products are going to coalesce together in little tiny lipid droplets that are called micelles. And micelles are going to be absorbed by passive diffusion. All we need is the concentration gradient. So no carrier protein, no ATP, no sodium, no potassium, just a lot of it. And that's why, since there's no carrier protein that's involved, it's not easily saturatable, and we can absorb a lot. Once we absorb these, they're going to reesterify. We'll build them back up into the triglycerides, into the phospholipids, the cholesterol esters, and the smooth endoplasmic reticulum. Remember, smooth like butter. So our lipids are going to be remade in the smooth ER. Now we have to transport them. So we're going to be transporting them by special lipid transporters that are called lipoproteins. Our lipoproteins include chylomicrons, VLDL, LDL, and HDL. With chylomicrons, that's made in the small intestine, and it carries mostly triglycerides because that's most of what we are eating. It carries only exogenous lipids. The source of these triglycerides and other lipids that it's carrying is, of course, going to be our diet. And so its job is to deliver triglycerides to muscle and adipose. And it's able to do that through activation of an enzyme that's called lipoprotein lipase. So lipoprotein lipase is essential for deposition of triglycerides into cells. So to get it into cells, you have to activate lipoprotein lipase. So what lipoprotein lipase does is it'll break down triglyceride that's in the chylomicron into glycerol and free fatty acids, and there's a special apoprotein that's located on chylomicrons. It's called ApoC2 that's going to activate lipoprotein lipase. So it senses that this triglyceride-containing molecule is close, turns it on, break down the triglycerides, get that triglyceride out of the chylomicrons and into storage. The next type of lipoprotein is VLDL. VLDL is very similar to our chylomicrons, except it's made in the liver. It carries mostly triglycerides again, and the source of this is our exogenous and endogenous, so what we make in the liver as well as what we get in the diet. And so its job is very similar to our chylomicrons. It's going to deliver triglycerides to adipose, and that's going to be through activation of lipoprotein lipase. It also contains ApoC2 that's going to induce lipoprotein lipase and cause breakdown of triglycerides into glycerol and free fatty acids. Once the glycerol and free fatty acids are inside muscle cells or adipocytes, we'll go ahead and reform them again and store them as triglycerides. Once VLDL gives up sufficient amount of triglycerides, it is now a triglyceride depleted molecule. It's called LDL, or low density lipoprotein. So your LDL is made from VLDL. And LDL carries mostly cholesterol. Its job is to deliver cholesterol to cells, and it's going to enter cells by binding on to a receptor. It's called the LDL receptor, and the entire thing is engulfed. And when we engulf this entire thing, it's called receptor-mediated endocytosis. And that's because it has a receptor ligand on it that's called ApoB100. Now once our LDL is inside the cell, we'll break it down, we'll digest it, and the digestive part of the cell is the lysosome. We'll break it down into little individual components, and then the cell can utilize those. Now, what in our diet can cause an increase in LDL. We can increase LDL, which is not good. We don't want to increase it, but there's certain types of fats, like excessive saturated fat can increase LDL, but also trans fat. Trans fat is by far the worst when it comes to increasing LDL. Our last lipoprotein is HDL. HDL carries mostly protein. Those apoproteins are receptor ligands and enzymes. HDL is made mostly in the liver, but we do make a little bit in the small intestine. Its job is known as reverse cholesterol transport. So what does that mean? Reverse cholesterol transport means we're going to pick up free cholesterol using that enzyme that's called LCAT, lecithin cholesterol acetyltransferase. And in that process, LCAT will make a cholesterol ester. So HDL cannot pick up cholesterol esters. It can only pick up free cholesterols. Cholesterol esters, if you remember, carry a fatty acid already on it. But we have to have a free cholesterol that has room for another fatty acid, because that's what the CAT part of it means. It's cholesterol acetyltransferase. So we're able to transfer fatty acid onto cholesterol, but only if there's room. So once we engulf that cholesterol molecule, HDL is going to take it back to the liver and tell our HMG-CoA reductase to go ahead and slow down, stop making so much cholesterol. We have plenty in our extrahepatic cells. No need to keep making more. So that's why we need sufficiently high levels of HDL so it can go pluck out that extra cholesterol that the cells don't need. Now, what in our diet can decrease HDL? Because that's bad. We don't want to do that. Trans fats will decrease HDL. It's the only type of lipid that's actually going to significantly decrease HDL. So we want to make sure that we don't overconsume on that, and this is one of the main reasons why trans fats are going to be banned starting next year. Hey, thank you very much.